So our second talk is from Professor Lingjie on neural representation and rendering of 3D real-world scenes. So Professor Lingjie Liu is the incoming Arvind K. Josh Indoor Assistant Professor in the Department of Computer Science and Information Science at the University of Pennsylvania, where she will be leading the computer graphics lab. Currently, Lingjie is Les Medina postdoc research fellow, working with Professor Christine Thibault in the visual computing and AI department at Max Planck Institute for Informatics. She received her PhD degree at the University of Hong Kong in 2019. But before that, she got her bachelor degree in computer science at Huazhong University of Science and Technology in 2014. So her research interests include neural scene representations, neural rendering, human performance modeling and capture, and 3D reconstruction. So let's welcome Lingjie.
Hi, thank you, Tuanfeng, for the introduction. Hi, everyone. I'm Lingjie Liu, now a postdoc at the Max Planck Institute for Informatics. It's my great pleasure to give this talk at AJ seminar about my recent work in neural augmentation and the rendering of 3D real-world scenes. Before starting, as I mentioned, as the Tuanfeng just mentioned, I'd like to share my personal update. I'll be joining UPenn as an assistant professor in next spring. And my lab will conduct research in the intersection of computer graphics, vision, and AI. Especially, my lab will investigate neural scene augmentation and the rendering of human characters and general 3D scenes. And in today's talk, I will talk about some of my recent work in this area in detail. I'm looking for a highly motivated student to join my lab. And also besides these great research opportunities, you will also like the traditional and beautiful campus of this Ivy League university. You will have a chance to see the world's first computer in our CS building, and also enjoy the city life in Philadelphia. So if you are interested, feel free to contact me. Now, let's go back to the talk. First, I will give you the motivation that attracts me to do this research in neural augmentation and rendering, and what is my long-term vision. As shown in this video, we live in a world that is 3D. Our activities, such as dancing, playing instruments, and interacting with the people and objects, are all performed in 3D. We digitize our world in 3D representations, and this allows us to visualize the real-world things from arbitrary viewpoints. This also helps us better understand the real-world things. For example, to help surgeons observe and make decisions during operations. And the 3D representations also allow us to interact with and edit the real-world things at our wills. Also, the future artificial intelligence should have capabilities to understand and interact with the 3D world for better behaving and helping people. Therefore, my long-term vision is to develop AI technologies that can perceive, understand, and interact with the 3D object, people, and environment. Specifically, my research will pursue 3 goals. First, high-quality reconstruction of real-world things, which are often dynamic. Our world contains a complex phenomena such as occlusions, motions, and interactions. And it's very challenging to faithfully reconstruct these natural but complex things. Therefore, my first goal is to achieve a production quality reconstruction of real-world things from sparse 2D images or videos as input. And given the reconstruction of real-world things, it's critical to synthesize like a photorealistic imagery indistinguishable from the real world and allow user control over like a 3D content. And for example, here, like digital object in the kitchen can be edited and recomposed. And here we can drive a virtual character to behave in the same way we do. Hence, my second goal is to efficiently synthesize photorealistic imagery of the reconstructed things and allow users to control like 3D contents. Next, we have seen like the success of machine learning in recent years, and this like the stats of machine learning has demonstrated like the importance of large-scale training data for learning powerful neural networks. And the developing AI technologies that can perceive, understand, and interact with the 3D contents also requires a large-scale photorealistic 3D data. But existing like high-quality 3D data is far from sufficient. Therefore, my third goal is to automatically generate a large amount of realistic 3D data and their corresponding imagery that can be used to train like the 3D learning models. Here I list some applications of this research area. For example, like AR, VR, moving industry, gaming, healthcare, autonomous driving, robot grasping, robot navigation and planning, and the human-robot interaction. Now I will explain why these goals are challenging. Modeling and rendering real-world things are two key problems in computer graphics and have been explored for decades. The classical computer graphics pipeline solved this as two separate problems. The automatic first, like if you want to synthesize photorealistic things, you first need to obtain the 3D model from your captured images. And the automatic way to do this is to apply like image-based 3D reconstruction methods, such as a structure from motion, multi-view stereo. However, this method cannot produce a very high quality result. For example, here, given 100 images as input, the reconstruction result is very noisy and has a large missing parts. On the other hand, like computer graphics rendering methods require very high quality 3D models as input for photorealistic rendering as shown on the left. Here we can see the gap between the output of the image-based reconstruction methods and the required quality of the 3D model for photorealistic rendering. And we can observe so normally like in the traditional computer graphics pipeline, we often involve some manual intervention in this problem. Next, I will introduce my work in modeling and the rendering of humans and the general static things to address the limitations of classical computer graphics pipeline. We will start with human performance modeling. We just mentioned that computer graphics rendering techniques requires very high quality 3D geometry models. But what if only like a coarse 3D geometry is available? How to achieve photorealistic rendering in this case? For example, if we want to generate like photorealistic animations of a person, so first step, we will like capture a video around this person and construct the human template with a manual correction that's shown on the right. Then we will manually tweak this 3D template to get the animatable human template. We then like drive this template to move by scanning and render the animated meshes using classical rendering techniques. But it's easy to see like this rendering is not photorealistic compared with the ground truth images. Like you can see, you cannot see like some dynamic wrinkles in this rendered result. And sometimes you observe for like some artifacts produced by scanning, for example, like the bumps under this arm. One way to improve the rendering quality is to fuse like a classical computer graphics components with the generative machine learning models. In recent years, this generative adversarial networks or GANs have made a great progress in photorealistic image synthesis. GANs are trained on like a 2D image dataset can generate new images that look authentic to human observers. But GANs are lack explicit 3D control in the image synthesis. For example, it's not possible to change like the camera viewpoint or edit the 3D content in the image synthesis process. In our work, we proposed to combine GANs into the classical human performance modeling pipeline for photorealistic synthesis of human actors under pose control. Specifically, given like a single view video as input, we first check the body motions in this video, then drive the animatable human template to move. Next, we render these animated meshes in different modalities like the rendered textures, depth images, and segmentation masks. And then we train a conditional GAN network to translate from this low quality renderings to photorealistic renderings. Once this network has been trained, at the test time, we can modify like the body parameters with the body motions from another person or from user interaction. So this method is designed for image synthesis from a single viewpoint. The next question is, could we extend this to free view image synthesis? That is, suppose we have like a multi-view videos of a person. What would be the result of training a conditional GAN network on this multi-view data? Here I show the result. The performance drops significantly. This is due to the fact that this model still optimized in the 2D screen space. So it's oblivious of a 3D geometry. One idea to address this issue is to directly optimize the geometry and appearance in 3D space. How to do this? And it turns out we can link like the reconstruction and the rendering part into an end-to-end pipeline by formulating like this image synthesis step as a differentiable physics-based rendering process. In this way, by comparing like these rendered images against the ground truth images, the 3D geometry and appearance can be optimized. And also like things like this rendered images that are enforced to be close to the ground truth images by minimizing the loss of function. These rendered images will be photorealistic. Based on this idea, we proposed a new method called real-time deep dynamic characters, or DDC for short. Specifically, like a given the multi-view videos of the person, we first check the body motions in these multi-view videos. Then we use the DDC to predict the geometry deformations in both coarse and fine levels, as well as the texture maps. And all these three components can be added to a skinned animated mesh. Then by comparing this random mesh with the ground truth images, these three components can be optimized. Once this human model is trained at the test time, given like arbitrary driving poses as input, DDC can generate pose-dependent dynamic deformations and appearance in 3D for new poses. And we can render the human from arbitrary viewpoint. However, a limitation of this approach is that it requires a person-specific human template, which means that for each person, you need to scan like the person from multi-views and construct its template and do the skinning. And this is a very costly process. Also, since we use the mesh in this project, the meshes have a limited spatial resolution, so we can observe some artifacts on the boundary. So, is there a better 3D human representation that is not person-specific and animatable, and also has the high achievable spatial resolution? The need for being not person-specific and animatable can be met by using simple, which is a skinned multi-person linear model. But a simple model is very coarse, even without closed modeling. So it's not suitable for modeling geometry details. On the other hand, Wisner work proposed the neural fields and demonstrated like high quality results in 3D modeling and novel view synthesis of static things. But these models are not able to model like articulated humans. In our Wisner work, New Actor, we proposed to incorporate the articulated coarse model, simple model into neural fields and design an efficient way to learn this new human representation. We first show a comparison to DDC, and with this neural field at the simulation, the artifacts on the boundary are gone. Before describing our method, we first take a close look to a representative work in neural fields, a neural radiance field also called NERV. In NERV, the entire thing is represented as a function that maps a point P on a ray along with a ray direction V to the color and the density at P. To synthesize the image, NERV densely sample point on each camera ray and accumulate like colors and the densities of this sample point on the ray to produce the color as a corresponding pixel. Next, by evaluating the L2 losses, the L2 loss between the rendered pixel against the ground truth pixel, this neural representation can be optimized. One main limitation of NERV is its slow rendering process. For example, NERV needs 100 seconds to render image at a 2K by 1K resolution. That is because the NERV needs to evaluate a large amount of sample points on each camera ray using this MLP. And we will discuss how to address this issue later in this talk. Nerve can only model a static thing, so we can use the nerve to represent the thing in a single frame. Next, how to extend the nerve to model animated humans. A naive way is to feed like a body pose parameters, for example, the joint angles as a conditioning to nerve. However, using pose as a conditioning leads to serious distortions as shown on the left. The main cause is that this model treats like each frame independently. That is, the network needs to memorize the full information of the thing in each frame. This is inefficient because we know there are shared and coherent information across different frames. That is like the shape and the appearance of the person in each frame would not change too much. Then what should be like the effective way to encode all this? In neural actor, we propose geometry-guided deformable neural fields that align all the frames into a shared canonical space. And we learn this shared space as a neural field. To align each poster space to the shared canonical space, we decompose the full movement into two parts. The deformation we presented by inverse kinematic transformation, and the pose-dependent residual deformations predicted by MLP. And this residual deformation cannot be covered by like inverse kinematic transformation. With this strategy, a dynamic sequence can easily be encoded and the result gets better as shown on the middle. However, this result is still blurry as compared to the ground truth. So what causes the blurriness? There are multiple causes, like complex dynamics of the deforming surface, also post-tracking errors, and the closed body interaction. As a result, the mapping from skeleton pose to dynamic geometry and appearance is not bijective. This mapping cannot be learned reliably using a deterministic neural model with a maximum likelihood objectives, such as our proposed model. One way to address this issue is to apply like a adversarial loss to prevent training from converging to the mean value. However, since the rendering of this neural field is very slow, calculating the adversarial loss on the whole image is infeasible. To resolve this blurriness issue, we propose to incorporate a latent variable to break this mapping into two parts. One from like a pose to latent variable, and the other from latent variable to dynamic geometry and appearance. Only the formal part is designed to handle uncertainty. The next question is how to choose the latent variable. As discussed before, this latent variable should ensure like the mapping from this latent variable to dynamic appearance and geometry to be a one-to-one mapping. We chose to use a texture map as this latent variable, which is aware of like the human structure. There are multiple advantages of using a texture map as a latent variable. First, during training for each frame, this texture map can be obtained by back project like the ground truth images to the checked simple mesh. This ensures like the mapping from the texture map to dynamic geometry and appearance in the ground truth multi-view images is a one-to-one mapping. The second advantage is that this texture map can be used as a local post representation. which means that for each 3D point P, we will find the nearest surface point at P and use these texture features from this texture map to infer the 3D geometry and appearance in the canonical space. Here we can see a lot of fine-grained details in this texture map. So this rich information would make the prediction of 3D geometry and appearance much easier. The third advantage of using texture map as a latent variable is that as we mentioned, that from pose to this latent variable need to be a many-to-many mapping. And this many-to-many mapping can be easily formulated as like an image translation problem that maps from like the normal map to this texture map. This image translation problem is well studied and it can be efficiently solved by the state-of-art like image translation network, such as the image-to-image or read-to-read. We can train this image translation network with adversarial loss to alleviate the uncertainty issue in this mapping. Now, by incorporating like this texture map as a latent variable, the result becomes crisp and also contains like the pose-dependent geometry and appearance in the result. Here we show a result of a neural actor. As we can see, given like the normal poses as a driving poses, neural actor can synthesize photorealistic animations of the character with the pose and view-dependent dynamic appearance, sharp features, and high fidelity wrinkle patterns. Besides the DDC, we also compared our method with the other 4 state-of-art neural rendering methods. And our method can generalize well to new poses that are very different from training poses, and also produce some like pose-dependent dynamic details. Here we show more results. Neural actor can like generalize to new poses. For example, this challenging dancing poses from the AIST dataset. Here we show like a free viewpoint video of the person controlled by driving poses. The body parts are well preserved and the dynamic deformations and appearance are properly synthesized. With a new actor, we can apply the same pose sequence to different people to enact synchronized crowd dancing, as shown here. Due to limited time, I will skip this slide. This is like a summarization of these 3 words. Next, we will move to like the general static scene modeling. And different from human performance modeling, no 3D information is available as input in this case. Our task is similar to before. That is, we intend to learn scene orientations from 2D images together with their camera parameters. And the learned representation can be rendered from arbitrary viewpoints. As I mentioned earlier, a main problem of NERF is slow rendering process. But actually, because the NERF need to sample a lot of a point in the 3D space, but actually most of these points fall in empty space and have no contribution to the ray color as shown on the right. So how to accelerate this rendering process? We note that the geometry shown in this figure is only for visualization. It's not known during training. So our key idea is to avoid sampling point in the empty space as much as possible. we proposed a hybrid representation called neural sparse voxel field, or NSVF for short, which combines the neural fields with the explicit representation, a sparse voxel archive. Specifically, instead of like modeling the entire 3D space into a single function as done in NERF, NSVF defines a set of voxel bounded neural fields to model like the local properties in each cell. You can regard like each cell as a local neural field. With the NSVF, we only sample point inside the non-empty voxels. Thus, the rendering process is more efficient. Besides like the efficient rendering, NSVF have two more advantages. First, NSVF stores like this distributed local information in each voxel. This leads to faster convergence of training and its capability of modeling large-scale things. Furthermore, the use of the explicit sparse voxels allows us to edit and compose the 3D scenes for image synthesis. Now you may wonder, if we don't know like this geometry during training, how to build this sparse voxel archive. In NSVF, we learn this in a progressive way on the fly from like a causal stage to a final stage. So starting from initial voxels, the sparse voxels will become more and more accurate and compact and converge to the ground truth geometry as the training progresses. And in each stage of NSVF training, we will sample point only in the remaining non-empty voxels and calculate the rate color by accumulating the colors and the densities of this sample point. We then compare the rendered images with the ground truth images to optimize this scene representation in this stage. And after this stage of training, we will prune the empty voxels and go on to the next stage training of NSVF. Here I show a comparison with the NERF. Our method achieves both higher quality and faster rendering than NERF. With NSVF, we can also interactively control the camera pose and synthesize novel views for large-scale indoor scenes. And I just mentioned one advantage of NSVF is that we can edit and compose more complex scenes at the test time. I'm glad to see like NSVF has inspired several recent work on faster inference, faster training, and large-scale scene modeling and editing. So far, we have shown like NSVF and the NERF can achieve impressive novel view synthesis results. You may be curious about the quality of the extracted surface from this learned representation. This surface are sufficiently like high quality for the purpose of a surface reconstruction. Here you can see like the surfaces extracted using marching cube are quite noisy. This is because like this method uses volume density as the scene representation, which lacks a constraint on surface geometry. Also, like existing like a neural method for surface reconstruction, such as the IDR, use like surface representation. But this method easily gets stuck in local minimum and also needs like a foreground mask as additional supervision. So we proposed like a new method that combines like the advantage of these two types of methods. So we use the surface representation, and then we use the volume rendering to learn this surface representation. Here we show like a comparison of our method compared to the baseline method. We can see like our method can achieve better quality. And our method is capable of reconstructing these challenging scene structures from multi-view 2D images. And here are more results. So far, we'll talk about how to reconstruct and render 3D scenes depicted in the input images. Now, let's consider how to generate new 3D scenes with the corresponding synthesized images. For this task, large data is needed to make the model learn like how to generate. Then what should be our training data? It's a multi-view images or single view images. Compared to like a multi-view images, single view images are much more easily accessible. How about the network model? And the 2D GANs that can be trained on 2D single view images and generate new images. But the problem of 2D GANs is that they cannot generate like the multi-view consistent videos of the same scene. Recently, we proposed the Generative, a method that combines the 2D generative models with these 3D neural implementations. Due to limited time, I will skip the details, but only show some results. Sorry. So Generative can be trained on like unstructured single view 2D image dataset. And this trained model can generate like photorealistic high resolution and multi-view consistent animations of new 3D scenes. This work addresses the limitations of 2D GANs in generating like multi-view consistent images of the same 3D scene. Due to limited time, I will also skip this slide for the summarization of these 3 works. Finally, I'd like to discuss the future directions of my research. So far, I have been mainly been focusing on neural modeling and rendering for either static scenes or humans. In the future, I'd like to explore modeling and rendering for scenes with interactions between humans and objects. This will require like the research on human and object interaction tracking, segmentation, and physics-based simulation. It also requires a dataset of human and object interaction for training these 3D deep learning models. I also plan to study generalization across the different person identities. We see a neural actor can synthesize a very high quality free viewpoint rendering of human characters under pose control, but it's unable to generalize to new human characters. So how to extend like existing neural human representations to generalizable models is another important and challenging problem. Another future direction is to synthesize large-scale 3D data for training. Currently, the shortage of a 3D dataset is a bottleneck for the development of 3D learning. I think one promising way to efficiently acquire more realistic data is by learning like 3D generative models from 2D single view image datasets. We have demonstrated like a Generative can like train the 3D generative model on 2D image dataset, but the current model failed to be trained on more challenging dataset. For example, ImageNet dataset, which contains very diverse things. So in the future, I'd like to explore how to train these 3D generative models on the ImageNet dataset. I'd also like to extend like this neural implementation and rendering techniques to other domains, such as robotics. Finally, I'd like to thank my co-authors. It's my great pleasure to work with them. You can check out my website for more details of the talk I presented today. And also, if you want to work with me, feel free to drop me an email. Thank you.
Yes, thank you, Lingjie, for the great talk. Yeah, so if you, dear audience, if you have questions, feel free to leave a message. So okay, so it's my turn to ask. Yeah, so I do have a high-level question here. So you talk about the application for neural representation in the robotics-related applications. So yeah, is neural representation or neural model a good thing for robotics applications? Because I thought it's like implicit, right? Like evaluate it in a larger scale probably will take time, which is like not that like directly useful like the previous approach like we have, for example, the mesh or something. So I mean, what do you see as the advantage of using the neural representation here?
Yeah, I think the one main advantage of using neural representation is that it's a generic representation, which means that you don't need to like define like the class specific representation. For example, in computer graphics, we often like define different kinds of specific representations for different classes of objects. And this neural representation is quite generic, so we can see it works quite well on like general things as well as very challenging things. For example, the scene structures. Previously, like I worked on like a scene structure reconstruction. You need to define a new representation for this class of object. But currently, this like I think the big advantage of this neural representation is it's a generic representation, and it's also very suitable for training. So it's a fit with like this differentiable rendering very well. And yeah, I think you already mentioned like the one disadvantage of this representation as well, like this representation, like the rendering process of this representation is quite slow. So this is like the problem, like a lot of research work on to solve this problem. And I think like in the future, we will definitely find like a solution for this problem, because for example, we can learn a neural network to sample point in 3D for this implicit representation. So to me, I don't think like it would be like a like inherent problem, but they would have a solution to solve this problem.
Yeah, cool. Yeah, I also feel like so when you generate the geometry, like you always need to like run some matching cube type of stuff. So that also makes this part like, of course, there are some like differentiable marching cube, but see, like usually it's not performs as well as like the classic marching cube, and it makes the whole optimization a bit.
I think it depends on your application. For example, if you want to extract the mesh, then you need to run marching cube. But for some cases, maybe implicit representation is enough for a lot of like applications, the segmentation or the grasping, robotic grasping, it's already enough. So you don't need to extract like the meshes as an explicit representation for the further post processing.
Yeah, exactly. So, Ari, do you have a question?
Very nice talk, really. I mean, amazing work you do there.
Thank you.
Hopefully you'll continue this also in the new place. I think in general, also in classical implicit modeling, one of the problems was really modeling of objects, like more semantic modeling. This is what I mean. So when you think about how people actually model objects, they assemble them based on parts, and they do, you know, and then they change the part and modify them and so on and create. So do you see any avenue of something similar happening in this type of approach? I mean, in a sense, so I mean, obviously, yes, you are solving gradually the capturing problem, right? So you can capture real models, and then you can then use nerves to represent them. Also motions. I mean, your amazing work on motion and everything. So hopefully video and motion. But going back, I mean, you don't always just capture things. You want to model, you know, imaginative things, more semantic things. So do you see any avenue of solving this problem using these types of techniques?
Yeah, I think this is a good question. There are some works already done like about this semantic segmentation. I think there is one work from Andrew Davison's group. So they would also predict the semantic labels for each 3D point. So in this way, like you can do like some editing based on these semantic labels. Yeah, I think this is like there are some words, but I agree with you. Like if we want to like to model and also like you recompose these things, we need like to predict the semantic labels in this framework, and also like to better understand like this kind of things with these semantic labels. Also in like the 3D generative models, if you want to generate new things, you definitely need to like understand each part of these things, so you can like generate new things with these fundamental like primitives, and yeah, to do these tasks.
Yeah, I was planning to ask the same thing here. So for your NSVF work, so is the voxels reusable? For example, like the voxels for one object, can you just like move it or duplicate it?
Yes, it's so yeah. The good thing of like this NSVF is it's a local representation, which means that after training, that you can like recompose these things. For example, you can put the voxels of this thing and put it on another thing, and then do some editing.
Yeah, so I do have another like more like technical detail question about your human rendering. So you use the texture map, right? But you have to like cut the surface. So you will create some discontinuity in your texture map.
Yes.
So would that like give you some artifacts when you put it back to the 3D human body?
Yes.
Like I mean along the seam.
We observe like this continuity along the seam. That is why we like cut the we define this UV parameterization by ourselves, not using like the default parameterization defined by the simple people. So yeah, we do observe like this continuity. So we did two things to alleviate this continuity artifacts in the without. One is that we define this UV parameterization, and the second is that when we generate the texture map, we dilate this area and impinge some like the pixels on the boundary region to alleviate this issue.
Yeah, but like your new, so the principle of your new UV parameterization is just to try to place the seams in the like less visible region of the human body, right?
Yeah,
but it's still,
yes. Yeah, but you still can see like this seam in the result.
Yeah. But what do you see as the, I mean, the bottleneck for improving the detail, the quality of the body synthesis?
Yeah, the currently like we are so we didn't like generate exactly the same dynamic textures that in the ground truth images, because we see like it's a very hard problem. So if like we do need to like so currently like we just minimize the distribution of like we generated the dynamic appearance that close to that in the ground truth. But in the future, I would say like if we can like more better modeling this process, and then like to modeling like how the clothes is moving and some physics simulation in this problem, maybe we can generate like a more accurate dynamic appearance.
But do you think is if it's possible that, say we just like use a super decent camera and take like super high resolution image and take so many of them, and of course like they were synchronized, like the humans not moving, or like in capturing a more like very sophisticated way. And is the current technology able to capture this type of information and to give you like a very high quality results?
I feel like currently the main problem is still lies in the algorithm design itself. Yeah, of course, like if you train this on like a more higher like images in higher resolution, then you can achieve like a better quality. It's definitely true. But currently, like for the algorithm itself, it still cannot like produce such a high quality in the ground truth images. So we still need to like look into like the algorithm itself.
Yep. Cool. So we don't have questions from the chat, and we're also a bit over time. So I guess we can stop here. Okay, so again, thank you both speakers. Thank you for the amazing talk. And I'd also like to thank the moderator from University of Science and Technology, China. And yeah, okay, thank you for your attention.
Thank you.
Thank you. Bye.
Bye-bye.
Bye-bye.